So if you've heard of quantum computing, you're probably asking, why should I care? Is it even possible? And what can it do for my business? In other words, what's the quantum value? Well, a significant application for quantum computing is in the advancement of a technology that you probably do care about, and that's machine learning. So if you're currently using machine learning, then quantum computing could have a massive impact on the way that you run your business and the products that you can offer in the future. It turns out that mainstream general purpose quantum computing is still several years away, but there has been a lot of progress in the field of quantum information processing, and that doesn't necessarily require a full-blown quantum computer. Such things as quantum key distribution, quantum number generation, cryptography, and the most exciting, which is quantum machine learning. Toridion's particular contribution to this field has been in the research and development of quantum random access memory technologies and quantum compression. And although we envisage that these emerging technologies were initially designed to assist future general purpose quantum computers to handle classical information more efficiently, what I'm going to demonstrate in this video is that we've been able to apply this technology to solving real world problems today. The results are dramatic. The speed-ups are in the order of millions to hundreds of millions of times for particular types of problems. And the reason for this is because Toridion's core algorithms are extremely error tolerant. That makes them very good at working with inputs, for example, that change frequently but only by small amounts, such as video. And this is a very desirable feature for many machine learning systems, such as perhaps absence of normal detection systems, where a classical machine learning algorithm would burn much of the processor time evaluating every input to determine if it was important or not. By contrast, Toridion's system can classify data in a much more elastic fashion with minimal training, so it suffers less error when input anomalies are present. Another feature is that it's linearly reversible, which allows a one-to-many and a many-to-one operation, which is much more in line with the quantum ethos, and it's also very desirable for certain types of applications in machine learning, and until today it's been quite elusive. Combining these novelties of design together, it's allowed us to implement very powerful applications ranging from database searches to principal component analysis, and much more recently solving intractable problems that have got direct implication to existing systems and some systems that you might actually use yourself. So an intractable problem is a problem that can't be solved by a classical computer, and they appear in many areas of our lives. They're exponential in nature generally, and it means that a small increase in the number of inputs causes a huge increase in the number of computational steps required to find the solution, or more importantly, the solutions, because it's often in optimization that there isn't an optimal solution, there's perhaps several. To demonstrate this, I'm going to show you a very difficult factorial problem that we're going to solve with quantum machine learning powered by Toridion. So let's take a look at what the factorial problem looks like and how difficult it is. An n factorial problem grows rapidly when you add more elements to the problem space. If you look at the slide, there's a set of tiles 3 by 3, and we can see that the n factorial of 9 is 362,880. By adding just one column and one row of extra tiles, the n factorial is now 16, and as you can see, the number of permutations has grown dramatically. The time complexity of a factorial is shown at the bottom, which is O(n) log n log n squared. If we add just one more row to this puzzle, so that we've got 25 squares in a 5 by 5 grid, as you can see, the complexity of the problem now raises to such a degree that there are over 1,500 million times 10 to the power 25 solutions, or individual ways that you can rearrange this grid. So we've devised a puzzle that's a little bit more difficult than that. What we're going to do is we're going to ask the neural network to memorize a photograph that's 10,000 tiles, and then we're going to randomize the image such that we ask the computer to rearrange the randomized tiles a bit like a jigsaw back to the source image. To make the problem more difficult, what we're actually going to do is we're going to present the original image to the neural network, ask it to memorize it, and we're going to store a very, very highly compressed version of the image in just 8 characters, so 8 letters. So this is going to be the equivalent of me asking you to look at this photograph once, write down 8 letters, and then we're going to cut the picture up, the original picture, into 10,000 pieces, shape them up in a bag, and then ask you, using only the 8 letters that you've got, to try and recreate the original image. And as you might recall from the complexity, we're basically the depth of the complexity on this is that there are more permutations than there are atoms in the universe. So from a brute force sense, it's an extremely difficult task. And because we've taken away the original image, there is nothing to actually compare against. So you've not got the box of the jigsaw to look at the photograph. We say, look at the photograph. Okay, write down 8 characters that you can use to try and remember how to put that picture back together. And then we take the box away, give you the jigsaw pieces and say, please put that back together. It's difficult to compare this problem to compete in this arena against a classical algorithm, for the simple fact that the classical machine would need an original copy of the image to be able to know that it's reached the right answer. But with the Toridion system, it doesn't actually need that information. The memory works in such a way that when it sees the correct pattern, its imagination is kind of frozen, and it creates an exception event where it actually knows it's reached the right solution without being told. It's categorically certain. From a performance perspective, the Toridion system was able to reconstruct this 10,000 piece jigsaw in a little over 20 minutes, and the time complexity was what we would call ON, which means that for every new tile added, or every row and column added, rather than it being an exponential increase in processing time, Toridion is simply just a linear addition. So if there's 10,000 pieces, it takes 10,000 steps. If there's 20,000 pieces, it takes 20,000 steps. Whereas conversely, the standard approach to the n factorial is obviously quite exponential. So how do you access this fantastic technology? Well, we have a prototype here. This is our networked attached quantum machine neural network. And you can access this through an API. You can put the appliance in your building, facility, and begin to use it. So if this overview has excited you to the possible applications of quantum machine learning for your business, we are working with selected industry partners. And for more information, get in touch at toridion.com.